We're about to start. Very so good and enjoy the show tonight.
Somebody's going to take our room over.
This thing on the side, is that the webinar? Or, yeah, so I should just leave it open there.
You can.
Or can I? Oh, yeah.
But you'll learn what you're going to see people questions.
Okay.
You can always grab more chairs on Friday.
Yeah.
Yes, so this isn't our floors, I actually don't know where they are, but they are.
Meaning New York. Modeling as well, but it's more for all the lighting to use. Part of
Okay, guys, I think we are all here, so let's get started.
Yeah, please. First of all, thank you for joining tonight and allowing me to share some of our knowledge and experience with the natural ventilation systems and how we are using simulations in the process of designing the optimal systems. Oh, now it's frozen. That's some of the agenda for today. I will begin with briefly introducing Window Master and the basics of natural ventilations. And then, of course, our reference case, House Zero. Then we will get into the main part of how we're using simulations to design and control our natural ventilation systems. And finally, I think maybe it was scheduled to be also after Rubina's presentation, but question if you have any, just interrupt me. And quick about the Window Master. We began as a part of the skylight manufacturer Velux, if you know them. They wanted a way to have automatic control of the skylights. And then later on, we started also supplying other window manufacturers. This led us to developing our own BMS system, which should be specifically tailored around natural ventilation systems. We are in many different countries, and in 2015 we were bought by Reboider, so now we are an independent company. Our main business areas are, of course, natural ventilation, but most of our projects is actually mixed mode ventilation because of the restrictions there are to natural ventilation, which is, of course, most of the time the outdoor conditions. Just some quick basics about natural ventilation. We have, of course, two main driving forces, which are the wind pressure and the thermal buoyancy. This leaves us with three main ventilation principles, which are single-sided ventilation, where you only have one facade with openings. And for this ventilation principle, it's important to consider that the windows will both be inlets and outlets. Then we have the cross ventilation, which is when we have windows or openings on two or more facades, and the stack ventilation, where we are utilizing the thermal buoyancy with the openings in different levels. The hardware we're needing for a great natural ventilation system is, of course, we need some window openings. We are normally suggesting having these openings highly placed and either top hung or bottom hung. This will minimize problems with draft, for example, and it can also increase the safety if the building is occupied by children, for example, mainly. We don't want any small hands to get trapped in the windows. Skylights is always an advantage because we can have more opening area and utilize the thermal buoyancy, the stack effect. The thing that makes it challenging with natural ventilation is that you will have to highly consider both the indoor and the outdoor conditions for temperature, CO2, and relative humidity mainly. We can also consider the pollutant levels, but we need sensors and a weather station to measure these parameters. And then we, of course, need a control system which allows for all the communication between sensors and actuators. Our reference case, House Zero, is a Howard retrofit project. It's an experimental building which are used for research, and this will allow us to get some great data on, for example, on this building we will have pressure sensors on the facade, which is not normally done on commercial buildings. And this will, as I will explain later, allow us to compare some of our calculations from the simulations with real data. It's a pre-1940s wood frame house, which there's a lot of these type of buildings in the United States. And one of the things that is important for this project is that the result is going to be applicable for the common types of this building. Yeah, some of the systems which are in work in House Zero are, of course, the natural ventilation, but there's also a sophisticated daylight autonomy, which allow us to have 100% daylight in periods where daylight is available. It will also have geothermal wells, which can provide us with radiant heating and cooling systems, which will be combined with the 100% natural ventilation. And then the building will have a sophisticated envelope with materials that can adapt to the seasonal changes. The ventilation concepts in House Zero is very important because there are possibility to use both cross ventilation and stack ventilation. But in the winter time, we of course want to avoid draft problems, and the radiant heating system will be active. So we will only use single-sided ventilation for this time of year, because this can, as I will explain later also, this can help us reduce draft problems when we have a very low supply temperature. In the spring and fall, we can utilize the full effect of the natural ventilation with both cross and stack ventilation, and we will have no radiant heating system active at this time. In the summer, we will actually go back to the same principles as we use in the winter time. This time we will have a radiant cooling system active instead of the heating system, of course. But to avoid humidity problems with condensation, we will still use single-sided or maybe only moderate stack and cross ventilation. The reason that we will maybe use some cross or stack ventilation is, of course, that in the summertime you will not have the same temperature difference between outside and inside, so the thermal buoyancy effect will not be as great. So we will mainly, when the radiant systems are active, we will have sufficient air through the natural ventilation system to have a great air quality. But the thermal comfort will be up to the radiant systems to provide. Some of the challenges that we usually experience in relation to the simulations of natural ventilation systems are how do I know that the natural ventilation system will be feasible for the building that I'm designing? Because if you are investigating this in a dynamic simulation program, it can be very time consuming if you have to model a 3D model with different windows opening and test out different opening areas. And then in general, how do I model natural ventilation in a simulation model, and in connection to this, can I just input the natural ventilation as a constant hourly air change rate? These are normally the restrictions we have, that people will turn away from natural ventilation because just the simulation process can get too complicated, and the risk will be increased of mistakes. So, but natural ventilation simulations are very important in relation to different areas. One is the compliance with the building codes. Right now in Title 24, that's actually not really a requirement for natural ventilation. There's more a requirement for the opening area used for natural ventilation. But one of the things that are important to prove with natural ventilation, and actually maybe the main goal of having natural ventilation, is to reduce or to increase the energy savings. And to prove that you will have energy savings, you will almost always need to do some simulations, because it's not often you have the luxury of replacing a mechanical system or reducing the size of it and implement the natural ventilation to have real data to compare. Then the simulations are very important in relation to the control of the system, because there's of course an increased amount of varying parameters when you take into the wind direction, the wind speed into account, and the outdoor temperature, of course, relative humidity. Then we will also need something as simple as where do we place the weather station to collect data. And at the last, one of the challenges with natural ventilation is, of course, thermal comfort. For example, we need to know how many hours a year we will have the critical conditions with natural ventilation. So the software we're using are in the beginnings to have an initial idea of the feasibility of the natural ventilation. We'll do some basic air change calculations. Then in many cases, we need some alternative systems combined with the natural ventilation, and we will investigate the need with dynamic simulations. At last, if it's needed to, for example, investigate the worries we have about draft problems, we will use internal CFD. The initial calculations we're using to find, for example, how much opening area is required to get the air change that we desire. And these calculations are very quickly done compared to if you are investigating this in dynamic simulation programs. And the thing with the opening area for natural ventilation is that you can get completely different flow rates depending on the ventilation principles with the same amount of opening area. So it's very important to consider if you're going to use single-sided or cross ventilation or stack ventilation, because you are able to achieve completely different amount of opening area. For the dynamic simulation, again, the natural ventilation, the supply temperature is going to be equal to the outdoor temperature. So it's very important to consider what climate zone you are in, and to find out what strategies you need to use in relation to draft problems, for example. So for House Zero, which are located in Boston, this will actually be a plot of our supply temperature. And one thing we can see without using dynamic simulations to find the number of hours of discomfort in relation to high temperature is that in the summer months, if we have a supply temperature above 80 degrees, this will of course not give us much room for cooling. So we will definitely have some hours with discomfort in some of the months. Yeah, and then we need to consider what we are going to use as an alternative strategy to deal with these periods with the discomfort. And in House Zero, it was dealt with radiant systems, both heating and cooling, and this allowed us to have a minimum operative temperature of 68.7 degrees Fahrenheit and a maximum of 79.7. degrees Fahrenheit. In other examples, we found that depending on the whether it's going to be 2 months of thermal discomfort, or 2 weeks or 2 days, we have, for example, found in Bullet Center that we have 2 weeks of discomfort, and in that case, it was the alternative strategy to deal with this discomfort was just to say in those 2 weeks you're going to wear shorts or t-shirts, because we're not going to implement, for example, mechanical system in a mixed mode system just for 2 weeks. So the dynamic simulations in relation to natural ventilation is very important to determine the alternative strategy, which are going to be combined with the natural ventilation system. Then, of course, this system will be, if it's a hybrid system or mixed mode system, it's very important for the cost and the indication. With natural ventilation, there's really not any maintenance cost. It's very minimal because it's only the actuators. You will need some lubrication maybe at some point, but really the maintenance is minimal. So it's highly dependent on what type of system you are combining with the natural ventilation.
I'm sorry, these figures based upon your house zero?
No, not this one. It's just an example of the.
Okay, I'm just kind of wondering where, what sort of a building would have as the cost basis, or is that just a comparison? This is just an example of a standard mixed mode system with natural ventilation and a mechanical ventilation system. But it's just to give an idea of how we are using the dynamic simulation to determine the strategies we're going to use. Yeah, one thing that's not considered often is the cooling we can achieve by air movement. Normally, air movement is something you connect with draft problems, but you can also turn it into a positive effect, because everybody knows that if you in the summer use a table fan or something, it will feel cooler than it really is, and you're not cooling the air, it's just the air movement. So you can achieve a lot of comfort if you are using the systems in the right way. This also applies to a winter situation, where we can use where we often use pulsing strategies to avoid draft problems. Here's an example. This is just a simple CO2 concentration calculations made, where we have an air change 2 times per hour of 3 minutes. And you are not really going to have any draft problems when you're only ventilating for 3 minutes. It will require longer exposure to cold air, even if it's 32 degrees outside. In Denmark, I'm located right next to a operable window, and right now it's below 32 degrees Fahrenheit outside, and with this pulsing strategy, it's more like just a quick slap in the face, or just a quick you get refreshed. It's not really it's actually comfortable if it's late Wednesday afternoon and you're getting tired. So you can use these, for example, this kind of strategy to avoid draft problems.
And I think it's also very important when you're talking about natural ventilation to consider the adaptive models, because if it's summer, you are not as exposed to high temperatures as if it's in winter. I think that's pretty logical. So I think when simulating natural ventilation for thermal comfort, I think the adaptive models should be highly considered. Yeah, for the internal CFD, it's again in San Francisco, you will never really have very low supply temperatures, but when you have low supply temperatures, which you can't avoid with natural ventilation because you can't heat up the air, you can be worried about different draft problems. So you can come a long way with the experience from earlier projects where you have gained the knowledge of when draft problems are occurring. But if it's needed, internal CFD is a very good way to check if you are going to have any problems. And in this connection, the type of window is of course very important, because for natural ventilation, the optimal window is normally a bottom hung or top hung window, because this is very good. You can place it at a high location, and you can get it further away from the occupants in the room. But if you're using side hung windows, for example, you are increasing the risk of draft problems to a high degree. So I would say that in the case with side hung windows, internal CFD would be it would be a high chance to be required to check if you would have any draft problems. For the one of the reasons that the side hung, that the bottom hung and top hung windows often will be the best way to use natural ventilation is of course the Coanda effect, and that's also why when we have a top hung window, it should optimally open outwards, so you will have the trajectory of the inlet air towards the ceiling. And this will also be very important if you are using a supply temperature of 32 degrees, for example, because this will be likely to cause draft problem if it's input directly into the occupant space. Here we can see an example of how large a difference 4 degrees of opening can mean if it's again, this is an example with an cold outdoor temperature, but it shows that 4 degrees of different opening area can have a really big influence on the indoor temperature. And this is where the control of the window actuators is really important. Mainly to control the temperature in the rooms, but it can also be a way to minimize noise problem and improve security if you're using the window for night ventilation, for example. Then we come to the last type of simulation that are very important in relation to natural ventilation. And this is the external CFD for our EMS system in the advanced. It's just as important as a temperature sensor or CO2 sensor for the system, for the control, to know exactly the opening degree that we require to have the desired air change rate. For House Zero, we are located in an urban location. Of course, if you are in an open field, it's pretty easy to predict the wind pressure. But when you are in an urban location, you need to consider the surroundings. Trees can, of course, be a bit tricky because they change with the season. So, yeah, mainly the buildings should be considered, but optimally all surroundings are very important. Here we can see the comparison of the first state of the external CFD model, where the trees are not highly considered. It's more the surrounding buildings, but later we will make some more accurate or detailed simulation models. This was what I was talking about in the beginning, that it's an experimental building, so we will have pressure sensors on the facade of the building to compare with the results that I'm going to show next. Yeah, the CFD models for the control of the natural ventilation system, we are doing from 8 as a default, as a basic. We're doing from 8 different wind directions, but this can of course be more detailed if required. It's depending on the surroundings, sorry.
So doing CFD in real time as part of your control?
No, it's not real time. We're just doing it to find the pressure coefficients.
Okay, so in this design phase, basically.
Yeah.
Not doing your part.
No, I think I've not experienced with it, but I could imagine that real-time CFD calculations would be challenging because the runtime is pretty long. I think these simulations take a few days to run. So but we're doing them to find the pressure coefficients, and we're doing it for only one wind speed, because the CEC or the pressure coefficients are constant. So when we have found them for every window opening on the building, they will not change depending on the wind speed, because they are really expressing the relationship between the maximum wind pressure you can experience at a certain wind speed and the actual wind pressure that is experienced on the facade. The reason that we are using, for the simulations, we're using 16 feet per second approximately, and the reason for this wind speed will mainly be because of the flow around the buildings, because of course at a lower wind speed the flow will be more tight around the buildings, and at a higher wind speed it will be more spread. So so we feel that 16 feet per second is a pretty good representation for both higher and lower wind speeds, and it wouldn't really make sense to start doing simulations at higher or lower wind speed, because it would just increase the cost and the benefits are not really great.
So it took several days for this external simulation to get the coefficient.
Yeah, I think the of course it depends on the computer on the capacity, but yeah, I believe they took a few days to run. I have here I have a part of the model, but it's actually including a bit more of the surroundings. But yeah, I need to watch a bit more, because I didn't make this simulation personally. It was one of my colleagues. So, but I believe he told me it took. Yeah, the last thing the external CFD is used for is the placement of the weather station. House Zero is a smaller building, so it will not be really as relevant for this type of building. But when we're dealing with larger building, it's very important where you place the weather stations to get a good representation of the wind speed and wind direction. We can see here that here we're comparing the same location of the weather station, but with a building surrounding and without. And the measurements from the weather station will not be they will not change very much, but we know that the actually pressure on the building where the windows are can change a lot. So this is an example of where you need to watch out for the placement of the weather station. Yeah, and here we have just a quick example of some turbulence we can experience at some part of the buildings, and then determining the wind direction will be very hard if you are locating the weather station in this type of wind turbulence. So it's very important to consider. Yeah, at last, I have just some thoughts to possible improvements, or just something that we experience is challenging when simulating natural ventilation, is partly the communication between different technologies, that because often you don't have a standalone natural ventilation system. You could have mixed mode on House Zero with radiant systems. So the communication between the different technologies needs to be correct to make sure that the activation is at the right moment, especially also when doing energy calculations, because otherwise you will not get the very well representative picture. Yeah, then as I showed before, a strategy, for example, like the pulsing ventilation, currently it's very hard to include in the simulations models, but it's very important in connection to the thermal comfort. And yeah, with the thermal comfort, as I also mentioned during the presentation, that the air movement is, if used correctly, is a great advantage of natural ventilation. It can be even in with a cold outside temperature. Yeah, so it should be, in my opinion, be included when considering thermal comfort. Yeah. I think that was all for now. So thank you for listening what I have to say.
So you showed an example of like a mixed or a hybrid building, but in a climate like San Francisco where the outdoor temperatures are lower, so if they get the ability to remove your air conditioning system completely with natural ventilation is like a lot more feasible. I guess my question is, you talk about like you showed the number of hours that will be comfortable. Do you have a sort of like a threshold to when you recommend to clients that they don't need air conditioning at all?
It really depends on the client, I think, because as I mentioned with the bullet center, where it was a decision to say to the occupant that you should wear shorts and t-shirts when it's too hot. That was the final decision was the client, because it's also a question of price, of course, as it always is.
Clients, like I tell the client, like you have 100 hours, that are above that.
Yeah.
And then like they're kind of just like, they don't always do. Sometimes like, oh, that's great. And sometimes they're like, I don't know what that means.
Yeah.
It's hard for them to like comprehend.
But that's also the thing with natural ventilation, that often it's not a surprise that if we are having more than 100 hours above 79 degrees, for example, because if the outdoor temperature is above 80 2 months of the years, it's not surprising. So it's more a question of what are you going to do. So if you're having 2 months with critical conditions, it would maybe not be fair to say to the occupants, just deal with it for 2 months, but 2 weeks is more sensible to do. And so, I think the main point often with dynamic simulations in relation to natural ventilation is to determine what kind of alternative system are you going to, and you can, in this regard, I am calling the wear shorts and t-shirt as an alternative system, but in many other projects, it would be including a mechanical system, of course, and then you could possibly use natural ventilation for 60% of the year, and that would still allow for great energy savings. But yeah.
Have you done dynamic simulation with natural ventilation and like the active radiance slab, like combined in one simulation?
Because if you have a mixed mode system with mechanical ventilation, of course, the two systems should work independently. You shouldn't have activated mechanical at the same time. But with the radiant systems, as I also mentioned, the radiant system is going to be responsible for the thermal comfort, and the natural ventilation system for the air quality. So you need both. And with radiant cooling, you can have problems with condensation in some. So that's also a very important part of the dynamic simulation.
And those two simulations would affect one another, right? You have your radiant system going and your natural ventilation system. Don't those by necessity have to interact as you're modeling?
Yeah, of course. And that's also the one of the hard things in the winter time with the pulsing strategies. That's also to avoid major heat losses. It's both
avoiding draft problems, but also in relation, you are installing or you are implementing natural ventilation to save energy. So you don't want to turn off the radiant system and then open the windows 30 degrees and let it all out. So of course it's the synergy between the systems are very important, and that's often what's hard to simulate. And if you don't have the experience, it can turn you away from using natural ventilation because it's getting too risky or too complicated, and so it can be a restriction or barrier. So
you're typically asking for use of usual weather data, like TMI3 data, historical, or do you also count climate change into your weather file? So the more extreme or heat-related periods generally increase of temperature in the next 10 or 20 years.
Oh,
a lot of these periods are really incorporated in some at the limit of the compound. So it would be interesting to see how do you deal with climate change.
Yeah, that's a good question. I think as a basic, if I should be careful how I answer this, but I think that we are not really considering climate changes because it can. It's also hard to predict what is going to happen in the next 20 years, but it depends on the location, because in general the climate change will maybe affect the average temperature of a maximum a few degrees, but in the specific locations it can vary a lot.
So I think that discussion about the TMI3 weather data, they should actually be up.
Yeah.
Because of the increase of temperature.
Yeah, but of course it's very, it should be, if it's possible, it should be considered, because the building will be here and there. But of course,
like maybe with the backup system, for example, your radiant system, you can allocate space, you could put a small chiller in there or something.
Yeah, and of course it's also a matter of just changing the algorithm and the programming. You're not. It's not a question of replacing a whole big system. If you find that in 20 years that the temperature is different from when you designed the system. So yeah, but I think it's hard to predict.
Maybe adaptive thermal comfort standard helps you out a little bit there.
Yeah.
Adapt to that.
That's a good one. That's a good one.
So do most of the jobs you've seen that have been more successful from a thermal comfort standpoint and sort of cooling dominated climates, do they tend to always have ceiling fans incorporated into the design, or is, as a general trend, do you notice that? Or
No, not usually. Just you're talking about a normal ceiling fan for increased air. Not really. It's not that common. No, yeah. It's of course in periods where you have no temperature difference for thermal buoyancy and no wind speed outside, it could be maybe an advantage for extra driving force, but in general, again, it depends on the zone, how many hours a year you are experiencing with no wind speeds. But often I think we would take other strategies for increasing the drive, other than just using a ceiling fan.
Do you think ceiling fan can
Sorry, I think we can continue like interesting conversation later on, but like, we still have other.
Oh, yeah, sorry.
Case studies. So let's go to Martina.
Yeah, okay.
Yeah, hi everybody. So my name is Rubina. I work for ARUP in a group that's called Advanced Technology and Research. And I mostly do like wind engineering or environmental physics in my job. And I promised a case study. There's gonna be just one, I'm afraid, but like in a bit more detail, because I think I knew that they were talking about like the design of a building. So I thought we can maybe take the perspective more on the outside environment and how this interacts with the indoor environment. So I've actually spent a lot of time in the past thinking about natural ventilation because that was the topic of my PhD, but I was more focusing on the tools. And so I investigated, for example, like how Energy Plus uses the airflow network model and how the input to it may affect the sensitivity to the results. Or on the CFD approach, for example, if we would simulate the environment inside and outside separately, or when we can do like combined simulations. And again, there is a lot of input by the user when we deal with natural ventilation. So there is a lot of like uncertainty given, you know, like of the various parameters that are chosen from on the CFD side, from like turbulence models or convergence criteria type mesh. So that was more like a past experience. But when I think about natural ventilation, that's the picture I have in mind, because I spent a lot of time thinking on pressure coefficient. So I think on these curtains that move in and out because of the wind. And so I thought that was just a way to start. So what I wanted to talk about is more about tools and some open question about natural ventilation, and then move on into this case study. So why I think why natural ventilation for me is interesting, I think is a way to improve comfort and air quality and possibly saving some energy in a building. So there is a lot of motivation to actually use more natural ventilation, even if it's a challenge, because that means interacting very strongly with the outdoor environment and then therefore like somehow losing some control on like the air that we are like pulling in. So I think on a sort of engineering or like scientific point of view, it's interesting to see how this interface between the inside and the outside interact like all the time and try to kind of like understand and predict it. As we already said, like natural ventilation can be driven by buoyancy or by wind. And I think the wind side is quite hard to predict because there is a lot of component that would come into it. So if we think on that curtain moving inside the window or outside, actually to get that pressure on the window, we have a lot of passages to step through. So we have a local wind profile, and then this wind is passing through the city or through some obstacles, and then it's going to hit the building, and the way the pressure is distributed will depend on the building shape, which sometimes is very hard to kind of like understand how that pressure like is distributing without having complex tool to actually understand you very well. And then there is a question about the window shape and how much this is reducing the flow getting into the space. So there is a lot to kind of like explore into that side. And that, I think that makes using tools quite difficult because there is always a lot to understand. I think a few questions I think that are open about natural ventilation is one is we already mentioned it, is how to comply with local regulation and understanding if we can do a building that is only naturally ventilated or is that enough? Is that enough to guarantee that the building is going to work all the time as one? And how to support that, like to like prepare the proper work and stuff to actually get output. And then because we are importing some outdoor air, like how we control it with moisture and also pollutant. And then I think this is the kind of like other side of like the spectrum is what to do with infiltration. So Nathaniel and I worked on a project recently where it was in a very cold climate, and actually the problem was these doors that were infiltrating a lot of air and were cooling down the space. So it's not really a natural ventilation seems like we want air to come in, but it's quite similar to when we actually happen to have some air coming in and may disrupt the mechanical system. So just a couple of words on tools because we mentioned it, so I thought it was worth kind of like discussing it a little bit. I think there are several tools that we can use for prediction, from very simplified methods to airflow network models to then wind tunnel or CFD. And we can improve the accuracy to a certain extent, but then we also increase complexity and time that is required to actually do the calculations. A simplified model may look like very simple. So if we have like a room that is like the perfect shape on every manual, that's like great. And then we can get like a very quick estimate of how much air is passing through the windows. But we only get average value, and often these are single zone. So I think if we want to move into a multi-zone, a possibility is to use the airflow network models, which I think are largely used by energy simulation systems. And this would model the space into some nodes that are characterized by temperature and pressure, and then they are connected through the airflow. So that allows to actually model like different spaces. But yeah, and at the same, so we don't get a prediction of actually the airflow everywhere in the room, but we still get the flow that is distributing into the spaces. And again, we have a question of like where we get the input data from. So CFD or wind tunnel can be good sources for pressure coefficients, for example, as we just had. So CFD is a good tool because it can test different options and then yeah, can be reiterated into the design process, and provides quite detailed results in every single point. So it's kind of like gives a good description of the flow. But there is like large cost involved, so I don't know if real-time CFD is happening already or if it's going to happen soon, but that's an actual question of like how much time do we need to kind of like get the results through. And I wanted to mention wind tunnel testing as well, because I think I'm not aware of a lot of like natural ventilation studies carried out in the wind tunnel because of several reasons, and I think one is scaling. But often, like in practice, a lot of buildings would have a pressure cladding study for going on construction or for the facade. So that's actually a good source for pressure coefficient, even if the reasoning for carrying it out is a different one. But then there may be like a testing. For example, for like odd shapes or very tall buildings, it's very, very frequent that actually these data are available. So that can become used then later on in the design. So the project I wanted to talk about today is a store in Mexico City. And the question is, how can we design for natural ventilation when we actually have air quality concerns as well as for the climate? So what we did for this project was to first set up a framework where we could work with. So understanding the local climate, understanding the local air quality, and how we would expect the internal air to distribute into the space to kind of define some boundaries. And then with that, we went back into like a weather file basically, and then try to get the potential for natural ventilation throughout the year. So I don't know if you're very familiar with Mexico City. I wasn't before going there. So Mexico City has a mild winter and very hot summers. So there is a potential of like overheating. And it's not very windy as a place, or it doesn't look very windy from the weather data. And during the winter, there is a thermal inversion. So like the air gets kind of like trapped near the ground, and it's very difficult for, especially for pollution, to actually raise up and be released. So mostly the concern for air pollution is during the winter season when that happens. This is just to show like wind roses throughout the year. So the first thing we did on this study was to carry out an external CFD to understand the environment around the store and what could have been the wind environment around it. So this is actually a representation of pedestrian comfort, but it just shows that this is our building, the gray one. And you can see that it's located in an area that is predominantly very calm in terms of wind. So we have some air circulation, but it's not very strong. So we don't expect like strong gust wind passing through the door, because these doors may be quite big. So we don't want too much air passing through. We just like enough, but not too much. So this is just showing the exceedance of certain like low wind speeds. So when we say ideal for sitting, it means that it's normally mostly calm. And we can see that during the time of operation of the store, this building is always in a sort of like calm zone in all seasons, really. So together with this, we use the CFD simulations to understand the pressure field on the building. And we use these pressure coefficients for then calculating natural ventilation. So the second topic was about the air quality. This is just to put things in perspective. So Mexico City is not the worst that can happen. It's just like maybe like other places that are much more polluted than this. So the air quality index is an index that is accounting for, I think, 6 different variables, like and it's often used for like health, sort of air quality related with health. And we see that Mexico City is in a moderate sort of like air quality band. This is a little explanation about this index, so you can see for different values what's actually the meaning of it. So ideally, we would like to be in a good or moderate sort of like type of air quality. And so it's kind of like difficult sometimes to actually understand what's the air quality next to your site, even if we have an idea of the picture of the whole city. So what we did was we realized that there was like an open source database online for Mexico City. So we could capture the data for like 5 locations around our site and understanding what was the trend over the year of the different sort of like air quality indices. So we analyzed this data for the operation of the store, and this is kind of like the picture that we got. So for like 90% of the year, we are into this range that we were describing of like good or regular sort of air quality. And of course, you never know what's like the local situation. So we ended up recommending having some monitoring station to like sort of connect with the control system, but overall it didn't look that bad. And then the next step, once we understood the wind pattern and the air quality situation, was to kind of define some band of temperature where we think natural ventilation was actually feasible. And the store was a 2-story building with a connected internally, and the idea was to have a radiant floor at the ground level for cooling. So what we did was to take the 2 extremes for us, so a summer day with 80 degrees and not much wind, and then a similar situation like a winter day with like 60 or 65 degrees and also very little wind. So here is just like a section through the store, and you can see with imports the outside temperature and the pressure coefficient that we got from the previous CFD to see how we would expect the air distribution to behave inside the store and if that situation would have been acceptable or not without the additional system. So here actually the radiant floor was on, so it was a 60 Fahrenheit surface. So you can see that when the air comes in, that's a little bit cool by the floor, but then overall the temperature is too high. And on the right, you can see, again, these are the doors on the right-hand side, so you can see the air coming in, passing through the floor and then reaching the outside. So the conclusion of this is that at 83 that wouldn't work, at least as a preliminary study. So like we needed a lower band of acceptability. Similarly for the winter, this time we didn't have the radiant floor on, and we didn't have internal loads for this time, so we expect the situation to be better, but still it seemed like it was too cold when it's 65 degrees with a very low wind speed. So this helped us sort of like set up some boundaries in which we would then calculate the natural ventilation. So this is the results at the end. So what we did was to impose that we could only use natural ventilation when the indoor temperature was between 70 and 75, and the outdoor air quality was between regular or good. And what we can see here, because one of the questions for the designers, like, do we need a radiant system, and like, what's the advantage of actually having it? It's worth having it for this application. So we compared the results with only natural ventilation and with also the radiant floor. So what we can see here is that for about like 20% of the year, the air quality is poor, so we wouldn't be advised to use natural ventilation, like regardless of what's the temperature inside. And then for about 45% of the year, then the situation in the store is expected to be comfortable. So natural ventilation would be possible during that time. And what it looked like is that adding a radiant floor on top of it would only increase from 45 to 50%. So then it's more of a design choice if that's the only application, if that was worth it or not. But that was what we estimated. And then this is a similar picture, but just split by season. And I thought it was interesting because we talked about like the winter conditions in the climate and how like the pollution level is worse, and we could see it here as well, where in winter is like more on a 25% like the poorer quality situation. So in the summer and in the fall is much lower. So there is more potential for actually using natural ventilation during that time. I think I've rushed through it, but we were a little bit late, so I don't know if you have any question for either one of us or comments. And thank you.
Sorry, I missed, so you're showing those are the results of our energy simulation?
No, this is just like sort of like hand calcs. So we wanted to just get a picture of like what would we would expect to happen. So it's a combination of, so we got, I think, realistic pressure coefficients from the CFD, and we kind of like, it was a little like single zone space really, so that was quite easy to actually do some simplified calculation on that.
You're just comparing the gains from the internal loads, the envelope loads, compared to the radiant system or natural ventilation?
Yeah. So we estimated what would be the temperature inside through that, and then we imposed that like when it was too hot, then we would just use a system that would provide like lower that temperature. So we're still like on a sort of early feasibility type of study. So
for the simplified model, what are those equations came from? What are you list a bunch of
it was just like a I think it's a CIPSA guide. They have like single side and cross ventilation. It was just to show that you can get like quick sort of correlations to start like working out what's happening. But then for more complex geometries, then wouldn't apply. Like if you think on, I don't know, like a complex museum where like the shape is very weird, then it would just really not possible to use it that simple. Yeah, I think.
And for your air quality criteria, what are the resources for defining the good quality and bad quality? What are the resources for that?
I think there are some standards based on the country, because I know Mexico has used a similar standard, but I think the values of reference may be different from the US, from what I understood. Taiwan personally don't like to get the air quality data kind of like acquired, but that's what I gathered from that. And as in terms of sources, this was just a database of the government. I don't know which agency of it, but like was just
hourly data or daily?
Was hourly data, yeah. And then like come up with like lots of weather station of air quality monitoring station. So it was quite. We could get like 5 quite close to the side. Like I think that the weather station is at the airport. That was much closer in terms of like describing the place. Okay. Thank you.
Feel free to talk to the speakers. We are, let you go. Hopefully, invite food. I think there's some salad left, so if you still hungry, feel free.
I'm sorry, but